All right, so here's another example where we're asked to integrate, this time 1 over the square root of e to the 4x minus 1. Now when you're deciding which integration formula to use, so of the three that are listed in this section, there's two that you might consider. So one of them says integrals of the form 1 over the square root of a squared minus u squared is equal to inverse sine of u over a. And then another one says integrals of the form 1 over u times the square root of u squared minus a squared du is equal to 1 over a inverse secant of u over a plus c. And then in both of these formulas, a is some number and u is some differentiable expression of x. But a is the constant. So I said in the previous video that in order to distinguish between an arc sine and an arc secant integral, the key is not whether or not the u is out front. The reason that you can't count on seeing that u out front is because often u and du have a common factor. And that's been simplified out of the expression in the integral that you're given. So you don't necessarily, you can't count on seeing this u out front because it may have been reduced out of the expression that you're looking at. And in fact, when you integrate integrals that are going to turn out to be arcsecant functions, you have to bring that factor back in. So a lot of times when you're integrating problems like this, you'll have to bring in some factor in the numerator and denominator to get it in this form. So that's something worth noting. So now when we're choosing which of these formulas to apply to this problem, so the thing to focus on is your expression of x, that's your u expression. So this is your u squared, and this is your a squared. So under the radical, we have u squared minus a squared. So we're going to use this formula here. In order to apply this formula, though, we have to have the integral written in exactly this form. So 1 over u squared of u squared minus a squared du. And we don't quite have that form because we don't have that u out front right now. And also, so if u squared is equal to e to the 4x, something to note there, that e to the 4x can be written as e to the 2x squared. So if the u squared is equal to e to the 4x, sorry about the glare there from the laptop. It's a kind of rudimentary setup I have here making these videos. But if u squared is equal to e to the 4x, then u is equal to half of that power of e. So u is equal to e to the 2x. This is your u squared, then u is e to the 2x. Okay, so u is going to be e to the 2x in this problem, which means du, I think I'll use a different color, du is equal to, so derivative of e to the 2x would be e to the 2x times 2. So 2 e to the 2x dx. Now, so we want to have our expression in terms of u times du. The du is all of this. So what I'm going to do, so remember I was saying over here that often u and du have a common factor, which we need to bring back into the integral. It's been reduced out, we want to bring it back. So I'm going to multiply numerator and denominator by this 2 e to the 2x. I'm trying to bring back the u in the denominator and the du in the numerator. So I guess let me write this out down here. So here's the original integral, 1 over the square root of e to the 2x squared minus 1. Let me leave a little space here. So there's the original integral. I'm going to multiply by 2 e to the 2x in the numerator and in the denominator. It's not going to look pretty, I guess. Squeeze it down there. How's that? Yeah, it's a little hard to see. Sorry, guys. Actually, let me write it out. So this is going to be 1 over So like I said, I'm introducing 2e to the 2x down here. Square root of e to the 2x squared minus 1. And then I have this 2e to the 2x, which I'm dumping over, on the back here, because that's where I want the differential to go, right? That's where I want the du to end up. So multiplying by 2e to the 2x in the numerator and denominator, and I still have the dx here. Now, my lids are all messed up. So now 2e to the 2x dx, that's exactly equal to du. So there's my du. This is u squared, so that's good. E to the 2x is u. So this right here is equal to u. This is equal to u. So what we have, okay, I'm going to use the bottom of the board here, is the integral of 1 over 2 times e to the 2x, which is equal to u, square root of u squared minus 1, and then this whole 2e to the 2x over here is equal to du. So this 1 over 2 is a constant coefficient. I'm going to pull that out. And now it has exactly the form that's listed up there. 1 over u square root of u squared minus 1. So in this case, a is 1 du. So the antiderivative is 1 over 2 times 1 over a, but a is 1 in this case, so I'm not going to write the 1 over 1. Inverse secant of u over a plus c, where the u is e to the 2x and a is 1. I should have written that way up here. But so u over a is going to be just e to the 2x. And this is your final answer. So one key here to take away, one key takeaway with this problem is when you decide that you need to apply this arc secant integration formula, you will often find yourself multiplying numerator and denominator by some expression of x, whatever your u is. Multiply by that in the numerator and denominator. That'll typically help you get this integral written in the form where you've got this expression of u that looks like that times du. The du is critical. Don't overlook the du. You always need to make sure that you have the differential in the back here, which in this case was the 2e to the 2x, before you can write it in terms of u and then apply the integration formula.